Hey, really exciting video. Okay, I don't do this very often, but this video was set up in literally the last few minutes because I've learned something and it's really important. Globular clusters. And this has made my day. Let me tell you why. Globular clusters are clusters of stars between 100,000 and 1,000,000 stars that are grouped packed quite densely together, but they sit outside of galactic disks, so they're not surrounded by gas or dust as in the rest of a galaxy. Now here's a really important point about globular clusters that I've just learned, and I didn't realize this. They experience zero anomaly to general relativity. They actually display Newtonian physics perfectly. There's not a single sign of dark energy or dark matter or any unexplained accelerations or gravitational lensing of light whatsoever. Now, why is that so brilliant for expansion theory? It's because every other theory in the world looking to explain the universe is putting constants into general relativity. And if you have a constant like lambda and a cosmological constant and MOND, modified Newtonian dynamics, you have a real problem if your constant doesn't then work in an area where there's a complete and utter absence of anomalies. So this actually is a smoking gun for a density-dependent universe as expansion theory predicts. So I'm quite excited. Let's just talk you some of the things that I'm learning, and I say I'm sharing this video pretty quickly. So globular clusters, tightly packed, 100,000 to 1,000,000 stars packed but sit outside a galactic disk. They orbit far above the disk in three-dimensional elliptical orbits, so they form these spherical halo populations tens of kiloparsecs away from the galaxy's center. There's no gas or dust. They're dynamically relaxed systems and they exhibit pure Newtonian, Einsteinian dynamics. There's no dark matter whatsoever. Now, why is that perfect for expansion theory? Because when we look at the density of globular clusters, they sit within a regime where there's no modulation coupling. It's in a region where we've got no coupling modulation or switches happening. There's no anomalous activity happening. So within the now frozen core fixed parameter set of expansion theory, this is a stable, high density region that fits outside of switchy technology, switchy gate technology. Okay, so it's in a high coupled state. So it's a perfect example of stable, uncoupled, master expansion, uncoupled regime. There's no density transitions and therefore no anomalies. Now, here's the big problem. So for the leading cosmological model of the day, lambda cold dark matter, it is a massive problem because there are no dark matter halos. They're not observed or needed in any way, shape or form. And that's a big problem for lambda cold dark matter, where they see dark energy, dark matter everywhere else in the universe that you look, except globular clusters. And it's because of the density, because of a density dependent universe. There's no unexplained accelerations. There's no unexplained speed about these globular clusters at all, like we see with outer regions of galaxy rotations. So under Lambda-CDM, the absence of dark matter or dark energy is extremely awkward, according to the report what I've got here. So that's a really deeply awkward step. Again, it is a major dilemma that lambda cold dark matter asserts that every bound structure within the universe is shaped by a dark matter halo, but globular clusters are not. That's awkward. That's kind of a bit of a dilemma. So, lambda cold dark matter cannot explain the absence of cold dark matter signatures in this one regime where the universe presence should be most obvious. The second leading cosmological model in the universe at the moment, MOND, modified Newtonian dynamics, predicts that gravity below a certain acceleration threshold acts and behaves differently, but globular clusters exist within this lower acceleration regime where MOND dynamics should kick in, but they don't. So globular clusters, especially the outer halos of galaxies, do have internal accelerations below the threshold of MOND, yet still follow traditional Newtonian behavior. Again, in the report I'm running, this is devastating for MOND, not my words. Devastating for MOND. Again, you can't apply a constant theory that doesn't apply in a particular region. So literally, I know I'm quite excited because I'm looking for the smoking gun. I'm looking for the evidence of a density dependent universe. I'm trying to spend my time on a pattern recognition work rather than the deep quantum field theory calculations and maths, which I prefer someone else to be doing alongside me, with me, rather than doing that alone. That's not my area. But I'm a problem solver and I'm looking for pattern recognition. And I've just found a really, really important pattern. Globular clusters behave normally when Lambda-CDM and MOND both predicts they should have dark matter and dark energy. An exciting development this afternoon on a Friday afternoon. Thank you for listening. Please subscribe. If you're watching Expanse Tension Theory for the first time, please go back to the original video filmed in an apple orchard, just for comedy, dramatic effect, because kind of Newton's apple, and watch the series. It's a development that's been progressing from an original idea of what gravity could be. That's where this started. It didn't begin anywhere else. It just began with an idea what could be a causal mechanism of gravity. And from that point, it's spiraling successfully, answering questions, answering problems. But globular clusters are a great find today. Anyway, thanks for watching. Bye-bye.